Guys, I am officially dressed, ready to teach you about the coronavirus. No, I can't do that. I can't even say it right. But I did want to go through and see if I could help you with this chapter. I want to make sure I say the right one. 13 on thermodynamics. So first, let me start to be able to breathe and not be so hot. All right, so let's go ahead and begin with going over our review questions. And you guys can grade those. It will be for 2 weeks because we'll show you the ones from last week and the ones that are due for this week. So I believe that's week 25 and week 26. All right, number one, ask, in a chemical reaction, where is the potential energy and where is the kinetic energy? So when we look at this, we know that the potential energy is what's stored in those bonds. Remember Lewis structures, how much you guys love those, tetrahedrals, trigonopyramidals, all of those. Those bonds store energy because when they come together, they have to do it in a way that, they're sharing electrons or transferring of electrons, and that's where all the stored energy is. When they release that energy to form a new thing, that's kinetic, obviously, because there's movement happening, and so that is where our answer is that it is could be released or possibly absorbed, depending on what the reaction is. All right, now, that one was worth 2 points, all right? And I think my 2 is up there, so that's good. Number 2, ask, if a chemical reaction has a positive delta H, will the beaker feel hot or cold? All right, so with this, it's like the cold pack, which I would have in class if we were together. When you break those 2 bags inside the cold pack and you smush them together, then you have, obviously, the cold temperature that comes out, and you can put it on wherever your boo-boo is, and hopefully it helps you. So that's a positive delta H value, and so that is energy being absorbed, so we would go through and say that would feel cold. Okay, number 3, where is a Hess's law more exact than using the bond energy law? I know I'm not reading the question exactly, but the idea is, and I have some problems that we're going to be looking at. I think this is number 1. Notice there is no phases, where if we look at number 2, there is phases. So having that phase written down in the equation gives you a more exact idea of what is happening to that reaction. So it is a more exact way to be able to find out the actual enthalpy of formation. All right, number 4 asks, what is the state function, and give 2 examples. All right, so this is one I sort of always refer to, like when you do on a test and you decide to cheat or look at your mom's answer key and you get an A and you don't care how you got that A, that would be a state function. It does not matter how you got there, it just matters with your end results. All right, so when we look at that, as one whose value is independent of the path used to get there. An example is when we look at enthalpy, which we're going to do that in a little bit, and Gibbs free energy. All right, so we have one more here. It says, which of the following substances will have a delta F, or delta enthalpy of formation of 0? When you went through and looked at those examples, you had to see ones that were an element all by itself in its normal phase. So it couldn't be anything that, for example, they give you O there, and that wouldn't be it, because O is not naturally all by itself. It's diatomic, so it always has to be together. So the 2 answers you would have is O2 and Cl2, because once again, those are elements by themselves. All right, so for week 25, for review questions, that is worth 9 points. All right, let's go ahead. This thing is really bothering me. Oh, sorry. Let's go ahead and look at the practice problems, okay? So the first one they give us is, they give us a reaction. I don't believe you had to write it down if I remember correctly. And they wanted you to find out what the delta H, or the enthalpy, would be. And so I put us off to the side here. Sorry, that's my cord for the TV. That this is going to be a bond energy type one. So you're actually going to have to go through and do the Lewis structures. And then once you find those, page 424 is the one with the chart for that. So let's see if I can go through. When we look at chlorine, all right, and join together. They each only need 1 electron. So because there is 2 of those, we need to put 2 of those down. All right. When we look at water, now realize you could put the dots up there, but in this situation, it doesn't really matter. All right. We have 2 waters again, and so we are going to have it look exactly the same. Okay. When we go over here, we have HCl, and with that one, it's once again, and I'm not worried, just like here, I didn't put all the dots around, not gonna put the dots around the chlorine here. And I'd like to ask and say, how many of the hydrochloric acid do we have? But I'd have to wait forever to hear you respond.
4.
So, thank you, Alex, that's 4. So, we would write down 4 of them. Now, if you knew it was 4 and you were just going to double the value or quadruple the value, that would be fine, but I'm just trying to show you everything. All right, and then I'm running out of space here. We have O2, which bonds like that because it needs a double bond to keep it happy. Once you know this, then you go back to the chart and you can write down the different values. So, for example, for this one, each one of these is 240. All right, kilojoules, per mole. You have 2 of them, so you put a 2 on the outside. All right, when we look at, you're just gonna look at like what that bond value is, which I believe is 459. I'm gonna run out of room here. And you would have to count up the number of bonds. So we have 1, 2, 3, 4. And you'd have to put a 4 there, okay? And then because my HCl's, I'm going to go ahead and write down here farther. When we look at my HCl's, we have 1, 2, 3, 4, and I believe that value is 428. Okay, and so we'd multiply that by 4. And then our last one, because there's only 1, it's not like you have to count a double one. You'd look in the chart and make sure you did it O with the double bond. And that one I think is 494? Yes, it's 494. All right, so a lot of written down here. I'm gonna go ahead and just subtract these to give you some idea. Notice I wrote here, you write the reactants first, which is what we have, and then we're subtracting, so I should have a subtraction sign, excuse me, and then the products. Be careful with your calculating, all right, that you end up not multiplying with the 2 times everything, that you can use your parentheses and go through that. All right, so altogether, your answer should be 100. Oh my gosh. Oh, let's see if Mrs. Barber can write that here. Kilojoules, all right. Yeah, 100 kilojoules. I believe you should still have per mole, all right. So when we look at that, that's a positive value, all right. We don't get a negative, and so that would tell you that it was an endothermic reaction. Not that you had to record that, but that's what you got. All right, number 2. So I believe in number 2, they actually wanted you to write the equation, all right? I went ahead and did this. The thing I didn't do, and hopefully you noticed, is I didn't balance it. All right, so let's see if we can go through. Here I have a 6, sort of squeezed in. I have 6 hydrogens, so I'm gonna put a 3 here. And I think that's gonna mess up my oxygens. Let's see, I have 2 oxygens, so obviously that's not gonna work. 12 here and 3 here. Yeah. So 12 plus 3 is 15. See if I can do that correctly. And 2. So if you remember, we want to get rid of this odd amount of oxygen. Then we can figure out even. So let's go ahead and make this a 6, okay? Which I know domino affects everything else. So now that I have 12 hydrogens here, I have to go back and put a 2 there, all right? And now that I have 12 carbons here, that means I have to put, let me move this arrow sign, 12 carbons there. And now let's see where we are with our oxygens. Okay, still just 2, But now we have 12 times 2, which is 24, and 6 times 0, or 6 times 1, I should say. So that gives us 6. So now we're going to have 24 plus 6, which means over here, because that's 30, we will need 15 oxygens. All right, so make sure you had gone through and balanced it correctly. And you're like, oh, maybe those are too big of numbers. Can we divide it through and sort of make it more simplified? No, because if you notice, that's a 15, not going to be divisible by the 2, which everything else would be. All right, I put here, this is a Hess law reaction because they gave us those phases. So we're going to turn and now look at chart on page 431 and watch this, watch this, watch this. Now it's products minus reactants. Not like our other bond energy one where it was reactants minus products. So please be very careful when you go through and do this one. Start here, 12 times, sorry, it took me a second to go through and read that, of negative 394. It's still kilojoules per mole, plus, and then I have to do the water, which should be a negative 242, if I remember correctly. Yep, 6 times a negative 242 kilojoules per mole. So both when you form these, they were exothermic reaction. And then you're going to subtract, and maybe it would help you if you did brackets, however you want to do it. You're going to do the benzene, which is 49, and multiply it by 2. And I think it gives you 2 zeros, actually. Kilojoules per mole. And when you come to this, oxygen is in its elemental normal state. So the value for that, 0. All right, so if you want to, you can hit plus 0, but not necessarily because obviously when you add or subtract with 0, it doesn't make any difference. All right, so when we go through our delta H of formation, make sure you put the F there because we're now dealing with Hess's law, and it's by formation, and that would be a negative 278 kilojoules. All right, so when you went through and did that, that would be your answer. Okay, so that's answer number 2. Number 3 says when coal is burned in a power plant, it usually contains a small amount of sulfur contaminants. It's like whenever you go by like a electrical power plant, it stinks sometimes. The sulfur burns along with the coal to make sulfur dioxide. All right, so here's our sulfur dioxide. If it's burning, it has to be in the presence of oxygen. And it says it's going to be turned into sulfur trioxide. Okay, so if the delta H of reaction, so they give it to us, we know that delta H is equal to a negative 198 kilojoules, if I copy that down right. Yes. Now they actually want to know what is the enthalpy of formation for this puppy up here. All right, so a little bit different. When we have this set up, we are now actually going to be trying to solve for our reactant value, which isn't too bad because remember, when we consider the O2, this basically gets canceled out because it's in its elemental form and it would be 0. So when we go through and rearrange this, we're going to add this to both sides just because I don't want to be negative. So it's going to be our delta H of reaction. It's going to be equal to the delta H, how about if I could write that correctly, a formation of the products minus the one of the whole problem there. So just a little arithmetic, okay? Go through and find this. So you're going to do 2 times the value of SO3, which is going to give you, I believe it's a negative 396. All right, and it's just 1, so we just have that. Okay, and then minus, which they already gave us, which is the negative 198. Okay. All right, then you go through and you can find that, Now there's a little bit of a tricky part, so watch me here. When we go to say, oh, well, that's our answer, be very careful because our one that we're trying to solve there was there was 2 of them. So when we go through and find all of this, we need to divide it by 2 because we want to know what it is per mole. All right, so when we go through, our final answer should be a negative 297 kilojoules. Whoa, that is an interesting J there. Sorry, guys. All right, and that's what you should get for that one as long as you make sure you divide by 2. I did not tell you the points for each one of these, but 1, 2, and 3 are each 2 points apiece. All righty, I believe that is the end for week 25. So if we add up our 9 points from review, the 6 points that we just got here, 6, see if I can make 6 points from here, we should come up with 15 points altogether. So on your homework, you're gonna put whatever you got over 15, and then you're gonna take a picture of that and send it to me so that way I can go ahead and record it. All right, please feel free to ask questions. If you're gonna make comments below this video, be kind, okay? Because I already talked to you about this is not my forte. All right, but please ask questions, text me. We'll try to talk, however it's gonna go through. And now I'm gonna go ahead and start a new video and do the work for the week 26. Bye, guys.